Welcome, developers. If you're looking to get your hands dirty with the Android Open Source Project, ASOP, for the very first time, well, you're in exactly the right place. Whether you're wanting to build a custom ROM, contribute to mainline, or honestly, just write better, more efficient apps by actually knowing what's underneath them, this is where it all starts. In this explainer, we're going to execute a complete, top-to-bottom dive right into the ASOP stack. We'll map out exactly how everything fits together so you can truly understand the structural foundation of the world's most popular mobile OS. Let's get into it.
You know, as an app developer, you probably spend most of your days working exclusively on the surface level, right? But for this, I want you to imagine stepping into a high-speed elevator. The doors close, and instead of going up, we are going to emphatically hit the down button. We're descending rapidly through the architecture you normally just build on top of, tracing the connections all the way down to the bare metal.
Think of this as our elevator directory. We'll start with a quick welcome to ASOP, then descend through the application layers, frameworks, and system services, the Android runtime and HAL, plunge down into native daemons and libraries before finally hitting the basement, the kernel foundation.
Okay, let's dive into this. Section 1. Welcome to ASOP.
So before we start descending, what building are we actually standing in? It's absolutely crucial to understand the difference between basic AOSP compatibility and full Android compatibility. See, AOSP provides a complete, highly functional mobile platform, but it has strict boundaries. As an AOSP developer, you're building the core platform, not the proprietary Google add-ons. Like AOSP doesn't include back-end cloud messaging services, or all those polished end-user apps you'd expect out of the box. An AOSP-compatible device just needs to strictly adhere to the Compatibility Definition Document, or CDD. But to achieve full Android compatibility, the kind you see on store shelves, a device has got to pass vendor software requirements and clear rigorous test suites like CTS and VTS.
So with that context out of the way, let's step fully into our elevator. We're about to pass through 5 distinct structural layers on our descent to the metal. Step 1, apps. Step 2, frameworks. Step 3, runtime and HAL. Step 4, daemons and libraries. And finally, Step 5, the kernel. Keep this visual map in the back of your mind as we drop through each level.
Ding! Arriving at the top floor. Section 2, the application layers. Now, this is the vibrant ecosystem where most app developers spend their entire careers. But even up here, not all apps are created equal. Notice we've got 3 distinct tiers. First, there's your standard Android apps, built solely using the public Android API. These are the third-party ones you download from an app store. Next up, privileged apps. These guys are pre-installed on the device and have special clearance to use restricted system APIs. And finally, device manufacturer apps. These are fascinating because they're heavily pre-installed and have direct access to unstable, low-level Android framework implementations. Because of that super tight integration, they can literally only be updated when the device's system software itself gets updated.
Wild, right?
Let's hit the button and drop one floor deeper. Section 3. Frameworks and System Services.
Welcome to the translator layer, and this brilliantly illustrates how the system securely organizes its toolsets to keep things stable. On one side, we have the Android API. That's your publicly available toolkit for standard third-party devs. On the exact opposite side, we've got the System API, clearly marked in the codebase as @System API. This side is strictly restricted to partners and OEMs for bundled applications. It's essentially the system's explicit way of segregating public developer tools from sensitive partner-level tools, so, nothing breaks accidentally.
Both of these APIs expose the foundational building blocks of the Android framework. Now, think of the framework as this massive, intricate collection of Java classes, interfaces, and precompiled code. But what's absolutely crucial to remember here is that this framework code actually runs directly inside the app's own process. It's not sitting on some remote server. It lives right there alongside your app logic.
But hey, the framework simply can't do everything on its own. To actually start talking to the underlying hardware, those framework APIs have to communicate with system services. We're talking highly modular, intensely focused components here. Things like System Server, Surface Flinger for handling complex graphics rendering, and Media Service for your audio and video routing. They act as these trusted intermediaries, doing the heavy lifting of securely managing device resources so individual apps don't end up stepping on each other's toes.
Moving down, we're leaving the framework entirely now and stepping right into the engine room. Section 4, Android Runtime and HAL.
Welcome to the Android Runtime, or ART for short. Listen, you can write the most elegant, beautiful, high-level app code in the world using Java or Kotlin, but here's the reality.
Your phone's processor doesn't natively speak those languages. It speaks binary. So ART has this critical, highly optimized job of stepping in and translating your elegant high-level bytecode into the precise, raw instructions that your device's specific physical processor actually needs to execute.
Now, what's really interesting about this next part is the hardware abstraction layer, or the HAL. Think of the HAL as the ultimate bouncer at an exclusive club. It's a strict standard interface that lets Android remain blissfully unaware of lower-level driver implementations. This is the sheer magic that allows you to write a single, unified camera app without ever having to worry about whether the phone running your code has a Samsung camera module, a Pixel module, or something else entirely. You just talk to the HAL, and the HAL handles all that messy hardware translation for you.
Leaving the comforts of user space abstractions behind, we plunge deeper into the native level. Section 5, Native Daemons and Libraries.
Down here, things get very technical and incredibly fast. We've got native daemons like init, which handles the entire boot sequence, plus healthy, logd, and storaged. And actively supporting them are core native libraries written purely in C and C++, like libc, libbinder for seamless interprocess communication, and libselenx for enforcing strict security policies. The crucial takeaway here? These daemons and libraries completely bypass those user space HAL implementations we just talked about. They possess the necessary clearance to interact directly with the kernel.
Let's take this down one final time, hitting the absolute basement of our skyscraper. Section 6, the kernel foundation.
The doors are opening and we are looking at the metal itself. So, the crucial point is that this entire stack we just descended through is completely grounded by the kernel. It's the central core of the operating system that physically communicates with the device's actual hardware components. To keep things highly modular and maintainable, AOSP actually splits the kernel into hardware-agnostic modules, which apply broadly to all Android devices, and vendor-specific modules, intricately tailored to the exact silicon running on the board. This brilliantly prevents Google and developers like you from having to write a completely custom OS for every single motherboard on the market. The generic pieces stay generic, and the vendor pieces handle the quirks.
Before we finish up, I really need to highlight a massive upcoming change to how this foundation is updated. Effective in 2026, Android is aggressively shifting its trunk-stable development model. They'll be publishing source code to AOSP on a totally new schedule, once in Q2 and again in Q4. If you take literally nothing else away from this layer, remember this. If you're building and contributing to AOSP, you must strictly utilize the Android latest release branch instead of AOSP main to ensure you're properly synced with this new platform stability cadence. Seriously, mark your calendars right now.
And there we have it. We've officially ridden the elevator from the top-tier user apps all the way down to the foundational kernel. As a developer new to ASOP, understanding this exact structural roadmap and how each layer seamlessly connects to the next is your absolute biggest advantage. So, now that you've successfully seen the stack from top to bottom, which layer of the Android architecture are you going to start building on first? Thanks so much for joining me on this explainer, and hey, happy coding!